Hey, this is the first video during coronavirus time, so I hope that we keep in touch with you, okay? And I try to make videos for you from day to day, so that you have enough materials together with the textbook. If you have any questions, just email me or set up a Skype meeting with me. All right. Uh, so today we learn about inner product spaces. In the previous chapter, we studied vector spaces. Let me remind you some basic facts about vector spaces, and then before we move to inner product space. So when we are talking about vector spaces, we were talking about like linear independence, uh, spanning set, basis, coordinates, and how to go from one basics to another basics. But basically, for a vector space, we need two operations. The first operation is addition, and the second one is scalar multiplication, right? And these two operations should satisfy, 10 properties, five for each. And then a set will be a vector space. And when we work with vector space, we didn't say anything about geometry of that space. Uh, the reason we didn't say about that because we don't have any distance. We don't know how to measure. Make sense? So we can think like, yeah, each vector in a vector space is a point, right? We know we know how to represent a vector as a linear combination of all the vectors, if possible. But we don't know how to measure distance between two vectors, between two points. And that is the main topic, in this chapter. So we will study distance between two vectors, between two points, and then based on the distance, we'll consider norms of vectors, and then we can measure the angle between two vectors, right? Uh, and then we can do a lot, with the distance. So we can determine based on the angle, we can determine if two vectors are perpendicular or not. If they're perpendicular, yeah, that's good. I think I explained you about that before about basics, right? So for example, this is R2. So if you have two orthogonal vectors, right? And in this case, they form basics. To work with them, perfect. I would say that, right? You might have another, non-collinear two vectors. They also form basics in R2, but of course, they are not really good. So we will study, all those things, okay, in this chapter, and then when we finish this chapter, we have tests on two chapters, 4 and 5, and then we still have two chapters in the future, linear transformations and eigenvalues and applications. But we'll do that. We'll finish that in 6 weeks. All right. So let's move to the first section of this chapter: length and dot product in Rn. Oh, mm, looks not very good. Okay. Length and dot product. So okay, let's talk about it. Rn. Okay, in Rn. But as usual, I will start from R1, R2, R3, and so on. So basically, in R1 there's we have straight line, right? We have straight line, and in here, the origin, zero element is zero. If you have any vector, means any number in here, so you can find the length of this, right? The length of this vector is just absolute of x. That is the length of vector x, right? All right. So if we move to R2, I would like to mention right here we need to consider absolute because x might be negative. So maybe in this side, so you have negative. negative length, just absolute of x. In R2, we know that from high school. So if you have any vector, any point here, A and B, right? And here's A, here's B. So we can measure the length of this vector. All that is the distance from that point to the origin. Okay? So the length in this case is equal to, let's say that is U. So I will write the length, I write norm, 2 parallelizing here, equal to square root of a square plus b square, right? Plus b square. So that is the length of vector u, or that is the distance from u to 0. If we move to R3, the situation is almost the same, right? I will give this picture, I will write here, so I just change this a little bit. I don't know if you can see this or not, but all right, let me see. I can erase this. I will draw picture in here, okay? Picture in here. So this is the z, this is x, this is y, this is z. If you have some vector, let's say x0, y0, and z0 in here, z0 in here. Okay, so we can measure the length, right? We can measure the length of this vector. Let's say this is u. So in that situation, the u norm equal to square root of x0 square plus y0 square plus z0 square. So it's pretty easy, right? Of course, when you increase the dimension to R4, R5, and Rn, you just add one more term in this sum, okay? Just one more term, like x0, y0, z0, or t0 square, and so on. But anyway, let's write out the formula for the case Rn, okay? In Rn, each vector can be represented as x1, x2, and so on, xn, right? And the length of x is determined by x1 square plus x2 square plus so on plus xn square. So that is the length of x. Or that is the distance from the point x to the origin, to 0 vector. Okay? So don't forget about that. Let's consider some example from textbook. So like let's say v equal to -1, 0, 4, and 1. So you can find the length of v, which is equal to square root of -1 square plus 0 square plus 4 square plus 1 square, right? So just simplify this. This is 1, this 0, 4, 4 square is 16. So I have 16 in here, I have 1 in here, I have 0 in here, I have 1 in here, and then I take square root. Overall, I have square root of 18. So that is the length of v, or that is the distance from v to 0. I want to mention about that several times because when you look at a vector space, each vector can be considered as a point. Okay, vector is a point. Don't forget that. Sometimes we look at those like a point. We measure distance from two points. So it's easier to say measure the distance between two vectors. All right. So here we have 4-dimensional case, but that's okay. Don't worry about that. If you look at this as a point, right, and in vector space, you always have origin. Okay, so this is a point V. You don't care about dimension of this picture. Just look at this line, 2-dimensional case, right? This is a point. This is 0. So that is the distance V. And of course, so you have some straight line here, right? You have some straight line here. So when you multiply, v by some number, by some scalar, so you just change the length. By this formula, if you have lambda v, where lambda is some scalar, and that is absolute of lambda, times the norm of v. Of course, in this case, lambda is real number, right? It's real number, so uh, it's real number. Now, for example, if you pick this v and you want to find the norm of negative 2v, for example, so I want to find the norm of negative 2v, right? Uh, we multiply by a negative, that means we just change the direction of v, right? In another direction with respect to the origin here. So usually you have to multiply negative 2 by, with all entries of v, but we don't have to do that. We already have the norm of v. Where's the norm of v? Oh, so I guess the norm of v should be square root of 18, right? Based on this, you just have absolute of negative 2, okay, times square root of 18. So you get 2 square root of 18. Is it? Or you can do, like as I explained, you can multiply negative 2, with all entries in here. So you get the following one: negative v, 2v equal to negative 2 times negative 1, and here 0 times negative 2, and here, negative 2 times 4, and here negative 2, right? So basically you get 2, 0, 8, negative, and negative 2. And then, you apply the formula again, you get exactly this number. Okay, this is about the length of a vector. And based on this, actually you can you can make a unit vector, from any vector. So here's the big truth. I'll give this example, and we just see that the norm of this guy is 18, right? So how to make a unit vector from here? Unit vector means, vector of norm 1, of the distance, of the norm, of the length 1. So basically, I would say, yeah, if we have unit vector, the length of that should be 1, okay? So from here, from this vector, I can make a vector, of the length 1 by dividing this vector, by this number, by the norm of that. So from here, from this example, I can have u equal to, v over norm of v. So this will be a unit vector. Okay, this will be a unit vector. So that is negative 1 over norm of v. Okay, I have number, so just plug in 18, 0, 4 over square root of 18, and 1 over square root of 18. No, numbers look horrible, right? But it's fine, don't worry about it. We need unit vectors. We need unit vectors. Let me explain you why, right? I just go back to our two case. So why we need unit vectors? Okay, in our two, you have two basic vector, right? This is 1, this is 0, this is 0, this 1. They have norm 1, right? They have norm 1. And when you express, when you have some vector x and y in here, right? And you want to find coordinates of x and y with respect to these basics, you see, you express x and y and you see the right way. It's x, y is just equal to x10 plus y01. So basically, x and y in this case are coordinates, of this vector with respect to this basics, where vectors are unit vectors. Make sense? So if you don't have unit vectors in here, you might just complicate, your situation. Let's say, if I don't want to use 1, 0, right? I use 2, 0, okay? I use 2, 0. So this vector and this vector still form basics in R2. But when you want to find coordinate of this vector, right, with respect to this basics, you will not have this form anymore. You will have x over 2. Make sense? And here y. So x and y are coordinates of this vector with respect to the standard basics. But with respect to these basics, where one vector is not a unit vector, so you change the coordinate. Of course, that is, it's not really a beautiful thing, right? So usually, uh, we try to work, we try to work with basics that have only unit vectors. Okay, that's the first thing. Um, and let's move to distance between two vectors. So now we already have, we know how to measure the length of one vector, right? I give this formula, okay? Let's move to the distance. I'll write in here 2 points, okay? Because we look at vectors at points. So now let's determine the distance. I would write, if you have two vectors uh, for u and v in Rn, okay, we can determine the distance between u and v. I write distance u and v, okay, that is just the norm of u minus v. That's just the norm of u minus v. So what's that? Uh, look at this triangle. Look at this triangle, right? So here's the origin. I have one point u, and I have another point v in here, right? So basically, I have two vectors, right? I know how to measure the distance from the origin to u. I know how to measure the distance from the origin to v, and I want to measure the distance between these two guys. Okay, so I consider u minus v or v minus u. That's okay. That's the same, right? But let's say u minus v. What is u minus v? If we use this triangle, this is vector u, this is vector v. So u minus v is this vector. Is this vector, right? So that means, the norm or the length of this vector is the distance between these 2 points. So that's why you have this formula. Make sense? So you have, sometimes you look at u and v as points, right? And sometimes as vectors. But in this triangle, u is equal to v plus this guy. But this guy is nothing but u minus v, right? This guy is nothing but u minus v. So that's why the distance, the length of u minus v is equal to the distance between 2 points u and v. All right, so let's consider the following example. Let's pick, u is 1, 2, 3, my favorite vector, and v is just 4, 5, 6. 4, 5, 6. So you can measure the distance between u and v. You take u minus v, okay, and find the norm or find the length of that vector. That is, let's say I write in this form: 1 minus 4 is 93, 2 minus 5 is 93, 3 minus 6 is 93, right? 93. So I need to find the norm of this. But what is that? Here you have 93, 93, 93. We can take 93 out, right? I will have the norm of 93 times 1, 1, 1. You see? But when you multiply with 93 in here, we just take the absolute, right? Take the absolute of this guy. And let me erase this picture. So this is equal to 3, the norm of 1, 1, 1. And we know the norm 1, 1, 1 is just 3 square root of 1 square plus 1 square plus 1 square. And finally, you get 3 square root 3. So that is the distance between these two vectors. It's pretty easy, right? You have formula, find the difference first, and then apply this formula to find the norm. All right. uh, I want to mention one thing with the distance, right? Very simple application of this distance. Uh, you you already learned, you already studied this from high school, but let me mention that in here. Let me erase this. So basically, the general formula of the distance between u and v is just equal to square root of u1 square, yes, minus v1, u1 minus v1 square plus u2 minus v2 square plus so on plus un minus vn square. Okay, so that is the distance. But now we want to write the equation of a circle centered at some point. Okay, so suppose I have this is u1, u2. Just consider in R2, okay, two-dimensional case. I want to find the equation of the circle centered at this point, and the radius is just equal to some number r. Okay, what does it mean? That means I have to describe all points in the plane, the distance from which to u is constant, right? The distance from each of them to u is constant. So I will use the distance formula, right? So using the distance formula, I need to describe all v, which is x and y, okay, such that the distance from v to u is constant and equal to r. Using this formula, I have distance from u to v is equal to square root of x minus u1 square plus y minus u2 square. And since that is a constant, so I put that equal to r. And then I square both sides, I get x minus u1 square plus y minus u2 square, and that is equal to r square. So you know this equation from high school. That comes from the distance formula. Okay. All right. So let's move to dot product and the angle between two vectors, and I think that's enough for today's lecture. Um, I bet all of you hear about this, and all of you know from calculus 2, 3, right? Uh, that's fine. So you have two vectors u, and you have another vector v. Okay, let's write in general form. U is equal to just u1, u2, and then un, and v is v1, v2, and so on, vn. You can determine the dot product between u and v, right? Dot product, that is just u1 times v1 plus u2 times v2 and so on plus un times vn. So basically what you do, you just multiply corresponding entries of u and v and sum them up, right? And sum them up. You get dot product of these two vectors. Make sense? Example. Again, let's 1, 2, 3, and v is 4, 5, 6. Okay, so you can find dot product of u times v equal to 4 plus 2 times 5 plus 3 times 6, and that is equal to 4, 10 plus 18, so will be 22. So that is dot product. dot product between two vectors. Okay, dot product has a lot of good properties, and we will see why we need dot product in the future, just very shortly. Okay, but let's list some properties of dot product and see. The first property I want to mention is from this formula, from this definition, you can see, you know, the relation between dot product and the norm of a vector. So if u and v are the same, if u and v are the same, here you have u1 means u1 square. So u2 square and so on, un square. Basically, you just go back to the formula of the distance between u and v, right? So I would say, yeah, that if you take dot product of u and u, right? So you have u1 square plus u2 square plus so on plus un square. What is that? That is square of the norm of vector u. You see that? Because the norm of vector u is with square root in here, and here without square root. So that's the first property, right? The second property, when you interchange u and v, of course, the sum will not change. So I will write here right away that is just equal to v and u, right? Dot product of vu equal to dot product of uv and vu, the same. Okay, next, you have dot product of u and v1 plus v2. So that is u dot product with v1 plus dot product with, okay, let me change this so you'll not be confused, right? So just v and w. So I have v and w in here. That means if you consider dot product of u with the sum of v and w, you just need to find two dot product between u v and then u w. That is very simple properties from the definition. So in case you have u1 in here, so you have v1. If you have a sum in here, right? So you have v1 plus w1, right? Plus w1 in here. So if you just distribute you for this out, you get two sums, right? u1 v1 and u1 w1. And so you can separate that and you get two dot products in here. Okay? Two dot product in here. Okay. And the third property is dot product of v is always greater than or equal to 0. This property comes from here, right? This always greater than or equal to 0. And the norm square is equal to 0 if and only if that vector is 0. That's it. There's nothing special. Okay? So let's do a couple of examples and then I think we can finish recording, and then I will make another video, for another topics in this section. So let's say we have u equal to -2, 1, and 3. V is 3, 4, 5, and W is -1, 0, and 2. So let's calculate U dot product with W and V, right? With W, V and W. So basically I have dot product with U and V plus U, W, and dot product between U and V is what you just multiply this guy, and this guy together and sum them up, right? So for the first, I would get -2 times 3 plus 1 times 4 plus 3 times 5, right? That's the first one. And then for the second one, I would get plus -2 times -1, 1 times 0, plus 3 times 2. So basically you get -6 plus 4 plus 15 in here, plus 2 plus 0 plus 6. Okay, so here you get 8, and here you get 19 minus 13, so basically you get 21. You know, it's not a big deal. Okay, so I think I stopped my recording here. Okay, in this, let me remind you again what we learned in this video. So first we learn about the length of vectors. Okay, second one, learn about the distance. Between two vectors. And then last one is we learn dot product. So I hope that the video is clear enough. But if you have any questions, feel free to contact me. All right.